Alright, so we'll start solving parts of the tutorial. We'll just give you hints how to deal with some questions, and the rest of the questions, as I said, you should solve them by the end of the lab period. Let's start with the first question. So assign formal charge to each atom below. As we have studied before, the formal charge of any atom, we just bring this a little bit closer. Okay. Now, the formal charge of any atom is equal, in any Lewis structure, is equal to valence electrons minus shared electrons over 2 minus non-bonding electrons. Alright, so let's see here this atom or the oxygen in this compound. As you can see, the oxygen in here, it is simply the valence electrons of oxygen from the periodic table is equal to 6 minus the number of shared electrons in here are 8 over 2 minus 0 because there is no valence, there is no non-bonding electrons, which equals to, in this case here, 6 minus 4, which equals to plus 2, which is highly unstable actually and unrecommended structure. So this is how we deal it. We just simply apply the rule here. Simply the formal charge is equal to valence electrons minus half shared electrons minus the non-bonding electrons. Let's see the carbon in this compound. So this is C double triple bonded and a lone pair in the carbon. In this case, the valence electrons around carbon, at carbon will be 4 minus shared electrons are 6 over 2 minus 2, which means it is minus 1. So the formal charge around carbon is equal to minus 1. Is there any question about the first question? Is there anything which is not clear about how to solve the first question? Alright, perfect. So let's go to the second question. The second question again is direct question. It's simply we have to circle the functional group in any compound and name it. So for this compound, we have OH here. Now, for this compound, we need to circle the functional group. There are several functional groups in this compound, as you can see. You can just simply, for example, I will choose 2 of them. This is here, for example, this is called phenol because the OH is attached to benzene. For example, I may choose this functional group. This here, it is amide group because as you can see here, we have a nitrogen attached to the carbonyl. And similarly, we should search for the other functional groups and simply circle them and write the name of the functional group. Is there any question about question 2? Any question? All right. So just please go ahead and do this. Now let's go to question number 3. In question number 3, we need to distinguish which pair are resonance structures and which pair are simply not. So in principle, the resonance structures, the resonance structure is just movement of electrons. In other words, atoms must not change. Atoms must be the same in order to be resonance structures. only movement here, or the only allowed to move, is just the charge, the electrons, nothing more, nothing less. Atoms are not moving. So let's just see the A and B from this question. Here you can see that in the A here we have this structure, double bond, and then CH3 plus minus, and we have this structure. When we view these two structures, don't worry, it's recorded, don't worry. Bayan, don't worry. Or Muhammad, it is recorded, the lecture, don't worry. Now, when we view this molecule, I'm just for the sake of double check. All right. Now, when we view the molecules here, the two molecules, we'll see that the atoms are the same. They are not changing. And it's obvious that this can be changed to that by simply either this pair of electrons goes here, and this goes there, and this goes there, or the lone pair at the nitrogen here can contribute to the benzene system. This bonding electrons can be here, and this pair can go to the carbon. So for sure then, this pair of molecules are resonance structures, and A, or the pair in A, is resonance structure. In contrast to B, if you check B, then CH2, double bond C, double bond CH2 with CH3, C, triple bond CH. Now, if you check here, you will see very obviously that this carbon is connected to two hydrogens. This carbon is connected to one hydrogen. Then therefore, right away, these are not resonance structures. They are different compounds. And simply, they are simply isomers or structural isomers. Do you follow me? So A is, or the pair in A is a resonance pair, while B, they are not resonance structures, they are simply isomeric structures. Is there any question about question number 3? Is there any question about question number 3? Any question? See here. I cannot hear you, sorry. Can you, Salma, can you please repeat your question? Sorry.
About question 3.
Yeah.
Can you circle more than one?
Can what?
Can we choose more than one?
Can you choose more than one, like what? I don't understand. You mean you want to solve more than 2? What do you mean?
No,
I don't.
choose like there's 2 or more than one wrong structure here, or it's only one.
No, I am just solving, as you can see, I'm not solving all questions. I'm solving, in every question, I'm just showing you how to solve the question. You have to continue C, you have to continue to check C, to check D, to check E in this question. Do you follow me, Salman?
Yes.
So if this is just, I'm just giving you the hint, I'm giving you the idea, how to deal with this type of problem, how to think of it, how can we solve it. But the rest, you have to do it, Salma. You have to simply practice and check all of the tutorial and do it and submit it by the end of the lab period, as we agreed.
Okay.
All right. Any other question? But I'm talking about the idea. I'm talking about the principle. Resonance structures, they are structures which the only difference in them is just the movement of electrons. Atoms are not allowed to move. Do you follow me? So this is the hint behind it. Got it? All right. Now, Hajar, you have a question? Wa'ad al-Abri, we just simply, according to the question here, you need to circle in question number 3, you need to circle the following pairs of structures that do not constitute resonance structure. So simply here, this B here, for example, is not resonance structures, while A is the resonance structure. That's it. This is what you have to do, Wa'ad. Got it? All right. Now, regarding question number 4, in question number 4, we need to rank the following sets of molecules according to acidity. Do you follow me? Now, in principle, acidity increases, or one factor to increase the acidity is simply when the atom directly attached to the hydrogen to be removed or to be lost, when this atom is more electronegative or becoming more positively charged. So that's actually the hint behind it. So as the atom becoming more electronegative, the atom directly attached to the hydrogen becoming more electropositive. So as the atom directly attached to the hydrogen becomes more positive or more electro or its electronegativity increases or more electronegative, then acidity increases. It is very simple aspect in here. As the atom attached to the hydrogen pull electrons or electron density from the hydrogen, it's easier for the hydrogen to be lost as H+, and thus acidity is higher. Got the point, guys? Do you follow me? Again, as the atom directly attached to the hydrogen becomes more positive, in other words, relatively speaking, becomes more electronegative, then the acidity will increase. Now, let's see the first question. The first question, we have a situation where we want to see the acidity of this hydrogen. CH2, Cl, then CH3. Now here we have CHCl, CH2 hydrogen, and then CH3. And then the last one we have hydrogen, CH2, then CH2, then CH3. I just separated the hydrogen just to show you. Now, as you can see in this example, now the carbon, all atoms directly attached to the hydrogens are carbons. So we cannot compare right away. So we need to check the other atoms attached to this carbon. You can see here, there is a carbon again, and again another carbon, and again another carbon. So we can just extend the comparison. But here you will see that the first compound here is attached to two halogens, to two chlorine atoms. each of the chlorine will withdraw electron density from the carbon because simply the chlorine is more electronegative than the carbon. And thus, what's going to happen? The carbon attached to this chlorine will pull electron density to more extent from this carbon. And thus, this carbon will pull more electron density from the hydrogen. Do you follow me? So this is simply the trend in here of acidity, as the atom directly attached to the hydrogen becoming more positive, then the acidity increases. Got it? So in this case, we should expect that this compound is more acidic than this, and this is more acidic than that, because this is here we have only one chlorine, while here we don't have electronegative atoms to pull electron density. Clear? So the trend here for...
Doctor,
Yes, please.
can you please repeat the example here?
Sure. But I'm just first, I will repeat the principle. The principle to determine, to compare acidity is very simple. Let's see, the hydrogen here is the hydrogen to be compared for acidity. And the atom here is any atom attached to this, right? The principle here, as the atom directly attached to this hydrogen becoming more positive, or there are factors making it more positive, then the acidity increase. Why? Because this atom will withdraw electron density from the hydrogen, and therefore the hydrogen can be easily removed or lost, and thus behave as an acid. Got the point, Al-Bara?
Yes, yes.
Perfect. So this is the principle here. Now, when we compare A, you will see that hydrogen in the three compounds is attached to carbon. So we cannot compare directly. We need to check further, or to compare further. This carbon is attached to what? And then further to what? Attached to what? Until we see a difference. Do you follow me? Now, you see here, in all of these, this carbon is attached to carbon, carbon attached to carbon, carbon attached to carbon. So here, the difference is there here. The second carbon here is attached to two halogens, chlorine atoms. We know that chlorine are more electronegative atoms compared to the carbon. Do you follow me? So what's going to happen, each chlorine will withdraw electron density from the carbon. Therefore, this carbon becoming like more electronegative, and therefore it will withdraw electron density from this bond. And thus, this carbon here will withdraw more from the hydrogen, and therefore the hydrogen can be lost or can behave as H+ in this case. Got it?
Yes.
Victor, we have for the third compound.
Yeah, I'm sorry. Oh, sorry, I didn't notice. It's fine here. So we have CH2 true, CH2Cl. Now, of course, yes, sorry, I didn't notice that. But anyway, the comparison is the same, because this chlorine will withdraw from this carbon, but it is far away from this carbon. Here you can see this is directly attached to that. Generally speaking, the inductive effect here, which is the inductive effect here, is simply the withdrawal or release of electron density via electronegativity difference. It depends on the distance. As this atom becoming closer to this carbon, the effect will be higher. Do you follow me? Maria, do you follow me? So that's why actually the comparison is the same here. So the same principle, the most important thing is the principle, guys, for acidity. Not just for this question. Anytime, whenever you want to determine or compare acidity of any species, one major important factor to rely on or simply to be directly related to will be always the ability of the directly attached atom to withdraw electron density from the hydrogen. Is that clear? Any question about question number 4? So the comparison in here will be, number 1 will be this, number 2 will be here, because we need to do it according to the question. So this will be number 3. All right. Now, for question number 5, rank the following sets of molecules according to basicity. Now, basicity is opposite to acidity. Do you follow me? Basicity is the ability of, one way of defining bases, as we said, for example, Lewis base. It's the ability of a species or molecule to donate its lone pair. You follow me? Now, any factor will affect to increase the electron density at this atom will definitely means the basicity will be higher. Do you follow me? Any factor decreases this ability, well, the basicity will be less. Let me just write it and then we discuss it. Regarding the basicity, any factor increasing electron density at the atom containing the lone pair will increase basicity. This is logic, guys. It's very logic, because simply when the atom has more electron density, it's becoming more electron rich, and therefore it can donate its lone pair. As this ability becoming less, the basicity will be less. Since this is a very only one question, please think about it carefully and determine what's the difference between these nitrogen. Which one will have higher ability to donate its lone pair, and why? You follow me? Okay, so let's solve it together. I'm not gonna solve it. Which one you think will be the highest basic compound? The strongest base. Which one will be? Let me just draw the sectors. We have CH3 C triple bond N, so we have lone pair here. We have CH2 double bond N CH3, and then we have CH3 N lone pair H, then CH3. All right. Which one you think will be the highest or has the higher ability to donate its lone pair? First or second or third? Last one will be, why Ahmed, the last one will be the highest species to donate its lone electrons, its lone pair electrons? Ahmed, because Ahmed answered the first. Ahmed, why should be the last one? Or Fatma, or Tahani, or Al-Mu'tasim, or Maria? You all said the last one. Yes, Fatma.
The single bond.
So what? What about single bonds? There is no reason here. So what? Single bonds or double bonds around it? So what? Why the lone pair here? The last one is correct, actually. This is the most basic. This is the second in basicity. This is the third. The weakest is the third one. But why? Ahmad, why? Omar, yes.
Because nitrogen will pull the electrons towards it from the hydrogen and carbon both.
But why? Why nitrogen will pull the electrons toward itself?
Because it has more electronegativity than carbon and hydrogen.
But all are nitrogens. This is nitrogen, has lone pair. This is nitrogen. What's the base based on Lewis acid and bases? The base is any species which donate a lone pair, isn't it? So this is base, this is base, this is base. The question is, which one is the strongest base, which one is the weakest base? All of the three, we have a lone pair attached to nitrogen. Aren't that? Isn't that true? What's the basic difference between the nitrogens here? All right. Now, what's the hybridization of this nitrogen? What's the hybridization? Exactly, Tahani. sp3, absolutely. This is sp3. What's the hybridization of this nitrogen? The second nitrogen. Absolutely, Ahmed. It is sp2. What's the hybridization of the first nitrogen? Absolutely, sp. So, what does that mean here? This is extremely important because actually plenty of factors in the future you will rely on your explanation on this idea, which is the hybridization and its effect on simply releasing electron density or withdrawing electron density. Now, when we say this is sp, that means the percentage of S in this hybridized orbital is 50%. This is the percentage of S in the hybridized orbital is approximately 33%. The percentage of S in this hybridized orbital is 25%. What's so special about S in this case? We said before in chapter 1, S orbital is closer to the nucleus, isn't it? Isn't that true? And therefore, the attraction forces between the electrons, these electrons, and the nucleus will be higher, will be stronger. So you can see, you can imagine here, that this nucleus will attract the lone pairs stronger than this attraction, and this will be the weakest. Therefore, the lone pair here can be donated to another species. Got it? Do you see now the effect of hybridization on basicity? Now, of course, this is opposite to the effect on the acidity. As you can see, just think about it. In acidity, it will be opposite totally. So here, generally speaking, basicity, you can just make this generalization. Basicity increases as S character, which is percentage in this case, decreases. When it comes to acidity, this is opposite to that. Acidity increases as S character increases. Do you follow me? Is there any question about question number 5? All right. So let's go to question number 6. Perfect. Let's go to question number 6. In question number 6, we need to draw in all lone pairs and provide the product of each reaction. Use curved arrow notation to show the mechanism. All right. Of course, sometimes if we don't show the lone pairs in any Lewis structure, this is your responsibility first to know it. So you should simply should have the feeling of how to draw a correct Lewis structure very quickly. Now, for the first question, for the first one, we have A. plus H2O. What's gonna happen if we have such a species? Of course, when I draw H2O, I just draw it automatically with the lone pairs, because this is what we used as organic chemists to do. That we simply draw the Lewis structure correctly and comprehensively. As you can see in your structure, in the question, the lone pairs here were not drawn. So you should first check the Lewis structures drawn there and write down any lone pairs missing from the Lewis structures. Now, very obvious, because every relationship in this life, every reaction is all about interaction between opposite charges. So we have a plus in here. So the only thing which may react with a plus, the plus here means electron deficiency, which means the electrons are missing in here. The lone pairs always means electron efficiency, which means this species has excess of electrons. Logically, what's gonna happen, simply the lone pair here, or one of the lone pairs, can make a bond with this atom. So what we're gonna get, we are going to get this reaction, oxygen and hydrogen, hydrogen. So remaining here, what will remain at the oxygen is one lone pair, and then the oxygen will carry a plus in this case. Do you follow me? That's actually the behavior or the trend of the reaction. That the lone pair at the oxygen will add itself to this carbon and make a bond with this carbon. طبعا the covalent bond, the new covalent bond which has been formed, it has been formed using the lone pair which was already or owned by the oxygen. That means the oxygen here will lose, like it will feel as if it has lost one electron, therefore it should carry a positive charge. Do you follow me? Any question about question 6? Sure. Okay. Let's go to who said D. Maria would like to solve D. Okay, let's solve D. So don't worry, actually, yani, if you understand the principles, you should never ever have any hesitation to simply confront any question. You should be very simple actually in this case. Anyway, let's go for D. In D here, what we have? We have a cyclic system like this. Yeah, plus and 1, 2, 3, 4. 1, 2, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. SH. Isn't it? So this is what we have in D. Now, first of all, we need to see, is there any lone pairs missing? Yes, we should know that the sulfur is like oxygen. It should be attached to two lone pairs. Right, exactly. Al-Mu'tasim, exactly. Now, again here, organic chemistry is a very simple topic, straightforward, based on one fundamental idea in the whole life. Attractions, simply always anything to happen in this life, it should simply happen because of the attraction forces. Attraction forces always occurs by or through opposite charges. Now, we have a plus, we have electron deficiency, we have lone pairs, we have electron efficiency. Right away, I should expect such type of interaction where the SH add itself to the carbon and make a bond inside. In this type of reaction, we call it intramolecular cyclization. The intramolecular, it means the reaction took place in one molecule, within the same molecule, as if the molecule is my hand, one of my fingers attack or simply make a reaction with another finger to make a cyclization within the same molecule. You got it? This is what we call it, intramolecular cyclization. Alright, I will show you now what's going to happen. As you can see, when this sulfur makes a bond with this carbon, there will be like a cyclic system which will be formed. And the cyclic system will be 1, 2, 3, 4, 5, with the 6 here. So what we will have here, we'll have here this attached to 5-membered ring, and this is sulfur. One of it will be a sulfur attached to a hydrogen and will carry a plus. That's what will be the product in this case. You see it, Muhammad? What will be the product in this case? Muhammad, can you see it? And everyone, can you see it? Right, but I want you to understand the idea, guys. I don't want you to just to know how to solve the problem. I just want you to know the idea, because once you get the idea, you should be able to solve infinite number of problems. We are not focusing on just one problem, how to solve it. We are focusing on the idea of a problem, how to solve all problems in the future. You follow me? Is there any question about question number 6? Perfect. Let's go to question number 7. In question number 7, to be honest, actually question number 7 is just a straightforward revision of what you have learned in General Chemistry 2101, which is simply in the last chapter actually of 2101. Now, you need just to look for the structure and just write down the hybridization and the bond angle in every atom. Now, I'm just going to look for atom number 1. What's the hybridization of atom number 1? What's the hybridization of atom number 1, guys? Exactly, sp3. What's the geometry around this atom supposed to be? Tetrahedral, absolutely. So what's the bond angle between, of course, check here, number 1 and the opposite one, the next one will be again sp2, sp3. So the one here will be sp3, the A, which is between sp3 and sp3, that means this bond angle is supposed to be approximately 109.5. Approximately around 109.5, exactly. Now B here, I think you should do it. I think we shouldn't spend more time on this. You should just do it by yourself. Yes, exactly. It is sp3, and then you should just continue drawing. You follow me? I'm just going to move to question number 8, because question number 8 you may have some new idea, but the rest is just simple thing. The angle in B. What's the angle in B? What's supposed to be in B? What do you think, Ahmed? Yes, perfect. Ahmed, perfect. It is less than 109.5. It's supposed to be, because oxygen in B has sp3, then the bond angle is supposed to be 109.5, but since we do have lone pairs, that means the bond angle in here is supposed to be less than 100. No, in B here, it's actually more than 109.5. Right? Actually, as it is written, sorry, it is less than 109.5, but the arrows is wrong. It's supposed to be between the two atoms. Yani, make please the atoms here this way. And oxygen, what we mean by, if we mean by this atom, this bond, this is supposed to be less than 109.5. because simply the lone pairs here will simply force these bonds to compress a little bit, because as we know, the size of the lone pair is higher than the size of any bonding pair. Yes, it is less than 109.5. All right. So let's move to question number 8, and question number 8 is about drawing resonance structures. In, for example, structure number 8, here we have O minus, double bond, O minus. Yani, we can draw different resonance structures. One of the resonance structures here, this can goes here and this goes there, till we may draw this resonance structure, O minus, double bond O. I'm sorry, it's becoming minus, and this is double bond O. And the third one, that this bonding electrons or this negative charge can make a double bond, and this pi electrons goes to the oxygen, so we'll have double bond O, and then oxygen minus, and then O minus, double bond O. These are the resonance structures which can be drawn for the A in question number 8. It's a very good question actually to all of you, just to practice more and more and to solve all the resonance structures. Yes, please. Omar, go ahead.
Victor, we have to write all resonance structures?
Yes.
Or just,
Yeah, no, all resonance structures. You should, whenever we are asking for all, you just draw all resonance structures actually. All right, Omar?
Okay.
Sure. So it's a very good question, but you know, just solve the rest of the problems if you wish. If you want, we can solve another one. Do you want me to solve another problem for you, or you can manage to solve it all? Okay, let me choose, for example, a C problem. D? Okay, D. All right. The D here we have NH2, double bond, and then CH3. And then we have a plus here. Of course, we should all know that the nitrogen in this case, like oxygen, it contains a lone pair. Do you follow me? So one of the resonance structures can be drawn for this species, that this double bond can goes here. And therefore we can draw this resonance structure. And this becoming a plus, double bond, this is CH3, and then this is NH2. Now similarly, another resonance structure can be drawn by moving this pi electrons to be this side, and therefore we will have it this way, double bond, and then plus is here, then NH2 is there, and then we have a methyl here. Finally, the last resonance structure can be drawn here, is the lone pair can be given here, and therefore we can draw the fourth resonance structure, NH2 plus, then we have double bond, and then we have double bond, and then we have a methyl. So as you can see, we may draw 4 resonance structures for this species, 1, 2, 3, and 4. Do you follow me? These are the all the 4 resonance structures which we may draw for this species. The question is, which one is the most stable resonance structure from the 4 resonance structures? Which one is the most stable and why, of course? Which one of these 4 resonance structures is the most stable resonance structure and why? Waiting for your trial, for your answer.
The last one,
Why? Why Omar the last one? Number 4. Why?
because there is no lone pairs, so there is no interaction within the molecules.
Yani you should always rely on the rules. What's the rule? You rely on it in order to determine the stability here. Exactly, Amani. This is as Amani said. It's the maximum number of bonds actually we do have in this resonance structure. Do you follow me? Or in other words, all atoms actually are reaching the octet. Therefore, this is supposed to be the most stable. So this is the most stable because number of bonds is the maximum, or all atoms reached the octet. Or simply because we have more bonds here. So either which is the same. Either which is correct and it's the same meaning. You follow me? So you just can solve the rest of the problems. Now let's go to the last question, which is question number 9. You follow? Now in the question number 9, we need just to find out no, Maria, it's better always to draw it separate, to draw just to move the double bond or the pair of electrons only once and then move the second time, the third time. Do you follow, Maria? Don't do it like just move it all at once in one arrow. Just be generous and draw more. Just move always one arrow at once back, because actually that's even more. You will be more sure that simply you will not make any mistake by drawing the resonance structures. Do you follow me? Okay, so let's take or solve one problem of question number 9, which is giving the IPAC name of the compound. So which one you prefer, A or B? Which one we should solve, A or B? Choose. Choice is yours. A. All right. All right, and as we said before, in the IPAC nomenclature of any alkane or any organic compound, first rule here, we must find longest continuous chain of carbon atoms. Do you follow me? And if you view the molecule here, you will see that this chain is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I think this is the longest chain. As you can see here, this is simply the longest chain of carbon atoms. Do you follow me? So the parent name in this case, since we have 8 carbons, it will be octane. Now, what alkyl groups are attached to this octane? We have here a methyl, we have here a propyl, and then we have here ethyl. In this case, we must start numbering actually from this side, because if we start numbering from this side, the first substituent will give it number 3, 1, 2, 3, 4. Otherwise, you'll give it number 4, 3, 4, 5, 6, 7, 8. So we'll have, if we write the full name, we'll have 3-methyl, 5-ethyl, and 4-propyl. So we'll start with alphabetic. So it will be 5-ethyl, then 3-methyl, then 4-propyl octane. That's the IUPAC nomenclature of this compound. Please make sure that you write it perfectly, comprehensively, by applying all rules. Never ever forget any rule of the IUPAC nomenclature. So write it according to all rules, including the punctuation rules. You follow me? All right. Is there any other question? I really don't understand, Ahmed and Ahmed, why you need more time, because you're supposed to use this time. It is the time of the lab. Until now, from now it is almost 3 up to until 5. You're supposed to finish it maximum within 1 hour, Ahmed. There is nothing actually to delay it or to postpone it. You just solve it right now and submit it by 5. What's wrong with that, Ahmed? Is there any reason really why we need to delay the submission of this tutorial? I personally, I don't see any reason why you should delay the submission. Difficult to draw? Alright. Anyway, you have this is just exceptional time because this is the first tutorial. You have until tomorrow 10 a.m. to complete the submission of this tutorial. Yes, you can of course you can simply how to submit it. You have the option. You can do it online. You can simply draw it by your hand, every question by itself, and make the answer. The most important thing is just to practice and to solve. That's it. You follow me? So as I said, I will extend the submission of this tutorial until tomorrow 10 a.m. But please, next time, just do the submission on time. Because as I said, this is just a practice. I want you to be involved in the training and the practice right away. All right. Thank you very much for your attention, and inshallah see you next Wednesday. يعطيكم العافية.